Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
Okay, so I have a setup here of what our problem looks like. So we have a triangle composed of three different layers. We have a segment here from B to A, from A to C, and then from C to B. And we are told that at points A and point C is an axis, and this triangle is free to rotate around the segment connecting A to C. So it can rotate this way around that axis. So this from A to C is the axis of rotation. And we are also told the magnetic field is to the right. We're given the direction of current. And all the variables that we're given this angle here is 55 degrees. We are given the current I. We're given the magnetic field B. And we have the sides, so we have three sides here. We have leg Y, we have leg X, and we have the hypotenuse, which I'll just call lowercase h. So we are given X. And we need to find the magnetic moment and the total torque around this axis. So first we need to analyze what we have happening here. So we have this magnetic field going straight to the right. And we have three different segments here. We can, right off the bat, eliminate this segment from B to A because it is anti-parallel, the opposite direction of the magnetic field, which would tell us that it has an angle of 180 degrees, which we know we'll be taking with our equation for torque. Tau is equal to, we have the number of coils, the number of times it's coiled or wrapped around, which in this case we just have one loop. There's only one loop here, so we only have to, we don't have to worry about n in this case, it's just going to be 1. We have the current times the magnetic field, and this is sine of theta. So when theta is in the same direction as or in the opposite direction as the magnetic field, our theta is going to be either 0 or 180. And we know that sine of 180 is 0. Sine of 0 or of 180 would give us 0. So this portion from B to A isn't going to contribute anything to our torque. Another thing we can see before we start punching numbers in is our axis of rotation is along one of our segments here, from A to C. So this, from our intuition, tells us that this probably won't contribute anything, and a good example of that would be trying to open a door by pushing on the side the hinges are attached to. It's not going to open in that case. You need to use where the handle is. That applies the most torque to your door to open it. Applying a force along this axis here won't cause any torque. It'll put a force on it, but it won't cause it to rotate. And we're only interested in torque in this case. So that eliminates two of our sides right off the bat. So we just have this one side left. I'm missing a factor here. This is also multiplied by the area. So there's a capital A in here. So this is the number of coils times the current times the area involved times the magnetic field sine of theta. So it brings us back to the area. What is our area in this case? So we have this segment here, which is the only one that contributes to torque. You can look at it as a one-dimensional contributor. It's only one dimension here. So how do we do area in one dimension? It's simply just the length. So our length from here to here, the length of h, is our area. It's a one-dimensional area. Typically, area is units of length squared. So you can have meters squared, you can have feet squared. Anything that's a unit of length, you can have units squared. But this is simply one-dimensional area. So all we need is the length in that case. That's all that's going to contribute torque to our tau here. So we've already eliminated n because there's only one loop. We have our current, we have our magnetic field, and we have side x. We need this length h. So we're going to have to use some trigonometry here. We have the angle and we have side x. So, which is the adjacent side, the adjacent to our angle. So if we take the cosine of our angle, which is 55, so cosine of that 55 is equal to adjacent over hypotenuse, or in this case, x divided by h. We know what x is, so we can find h by moving it to this side, so multiplying both sides by h, and then dividing both sides by this cosine 55, in which case we will end up with h is equal to x divided by cosine of 55. And that will give you the length of side h. Simple, basic definition of our cosine function. Cosine of 55. So x divided by cosine of 55 gives you this length. So now we have the length. We can put that in for a. We can simply just call a L in this case because it's just the length. So let's see if we have everything we need. Let's rewrite our equation for tau. Tau is equal to, we don't need n is simply 1, the current, times the length, which we can just call h, because we already know what h is. We have b, and it's sine of that angle, because this is only what we want here is the portion of this whole triangle that's perpendicular to this field. So we want the projection basically into this y-axis, because that's where the force is going to be applied to rotate around this axis from A to C here. So this will be sine of 55, and that will give you the perpendicular portion of this wire here in part H. And you can just plug in everything here, and that will give you your torque, tau. And there you have it.